Everyone. I guess we're live. Um, really appreciate everyone joining us today from all over the world. We have people from Nigeria, from Dubai, from the Philippines, from Arizona. So wonderful to have so many people joining us. I saw some people, I think, in Australia and New Zealand where it's midnight. So we really appreciate everyone's joining us for this webinar. So I'd like to welcome all of the space enthusiasts, the future astronauts, and indoor farmers who are joining us today. This webinar is being brought to you by Agritecture and Davi Souza. And we are also joined by a panel of experts who you will meet shortly. My name is David Caesar, and I'm the lead agronomist with Agritecture Consulting. And I will be one of your moderators for today's webinar. Next slide, please. So for those of you who are not familiar with Agritecture's work, I will give you a very brief overview of who we are and what we do. Agritecture is a consulting firm based in New York. We're comprised of a team of agricultural and engineering experts with a focus on urban and controlled environment agriculture. Agritecture was founded in 2011 and since 2014 has been offering consulting services. Next slide. Agritecture has worked on projects all over the world, as you can see, and this diversity of projects and project experience makes us a very valuable partner for your next project. And although we have worked globally, we have yet to do any work on other planets. We hope that this venture into space farming will lead us into that new direction. Next slide. Agritecture Designer is our farm planning software where you can accurately estimate costs and yields for your greenhouse, vertical farm, or container farming operation. Our crop database includes more than 100 crop varieties so that you can accurately plan your farm. Agritecture Designer is being used by all sorts of people, entrepreneurs looking to start farms, operators who are looking to expand, and even high schools and universities who are using it to provide CEA education. Please check out Agritecture Designer today. Next slide. Finally, I am thrilled and honored to announce that today marks the launch of our premium content through the Agritecture Designer platform. The premium content will feature unique and expert video content from experts such as Davi. Davi and I have been working closely together to get this first course launched for about the last year, and it will be the first of many online courses and industry reports and more which will be available through this platform. I want to thank Davi for his collaboration and hard work on this project. Now, I've mentioned Davi several times, but haven't given him a real introduction. Davi Souza is a Brazilian greenhouse specialist, researcher in ag tech and space farming, and a consultant with more than 6 years of technical knowledge and experience in CEA and indoor farming. He is currently an electrical engineering student at the State University of Campinas in Brazil. During his career, Davi has worked as a researcher and analog astronaut at the first space station in South America. He was an intern at a vertical farm and urban farm in Brazil, and also became a visiting student in Saudi Arabia to research advanced technologies for desert agriculture. Davi will act as both a moderator and technical expert for this webinar. Davi, take it away.
Thank you for your introduction, David. Hi, everyone. Well, good afternoon from Brazil. It's a great pleasure for me to be with all of you here. We already have more than 100 people, so I really appreciate your time to be here and learning more about space farming at all. So starting our webinar, I will provide you here the agenda. Basically, we'll cover what is the SF101 or the Space Farming 101. Then we'll have a roundtable with a few experts that are working directly with the topic of space farming in different, let's say, in different types of institutions. After that, after these questions, some introductory questions, we'll have questions from the public, from each one of you. So if you are interested to address your question for the experts here, feel free to do it. So David will be together with me checking in cases which are the questions we can address along this webinar. And finally, we'll effectively launching the course, providing you a really special gift for those who attended here today. Well, what is the SF101? Let me provide you a brief overview. But first, I want to let you know that this course didn't came from nowhere. Me, together with these experts that are here, we have been collaborating directly with a lot of space farming research, not only in academia, but some of them are involved with space agencies and also companies. You will know more about them here. But we figured out that a lot of knowledge is have been put along the years on the space farming topic. We can mention some initial studies on space farming in the 60s. And still, we have a few people that are aware of the importance of this field. That's why the Space Farming 101 came up as the first space farming online course on Earth. At least we are not aware of any other initiative like this as we are providing to you today. The idea of the course is to be dedicated to space farmers, space enthusiasts, growers, and CEA professionals, or people that are working directly with technologies for agriculture. The course also will be providing you real examples of space farming technologies, which means that you'll be presented to a lot of solutions that was developed and that is allowing us right now at the International Space Station to grow plants in space. The course, as David mentioned, will be available at Agriculture Designer, and it's part of the Agriculture Designer curriculum because you'll be able to utilize this knowledge to plan your own farm. And this will be part of the Knowledge Hub, in which you'll be able to also have access once you are integrated with Agriculture Designer platform. You also will have the opportunity to access other very interesting content there that will support you during the planning phase of your farm. Well, the course has 4 lessons with more than 2 hours of content. And specifically, we will have 14 dedicated modules, 14 modules with 2 dedicated case studies, providing you a better idea on the projects that has been collaborating to space farming research. And as David mentioned, I will be the instructor along this Space Farming 101 journey. And for me, it's a great pleasure to be part of this journey with each one of you. So what we'll learn along this journey? The lessons, these are just the big topics, the broad topics of each one of the lessons. First one, we'll present the importance of studying space farming. Then we'll have a better idea on how we can support life, human life in space with plants. And then we'll be able to go directly to the bunch of technologies that was developed for space farming, space cultivation. Finally, you'll be presented to the synergies between controlled environment agriculture, or CEA, and its space related, the SpaCEA, which some of the panelists here, the experts, were the responsible to introduce, even myself, this concept. And I'm sure that they will also provide you a better idea about it. As you can see, the modules are divided in each one of the lessons together with the case studies. And let me tell you that if you remain here until the end of this webinar, we'll be providing you a special launching discount. Now, let's go directly to this roundtable. I am sure that each one of you are already excited to know what these guys, the invited speakers, are doing. That will be an opportunity for us to know more from their side and from their experience and background and how they are collaborating with the topic of space farming. So, first of all, I would like to welcome Luke, Tarun, and Alexis. thank you for being part of this webinar today, and also for the great collaboration that we have been doing along the years. Me and David will be the moderators, and well, welcome you all. And now I would take the opportunity to ask Luke to introduce himself and what he's doing in the sector.
Okay. Yeah. Hi, everyone. So thanks, Davy. Thanks, David, for the invite. It's great to be here. I know you've been working on this for a long time, so it's pretty exciting to see it finally being launched. So it's nice to see some familiar faces in the chat. So looking forward to some good discussions. But for those of you that don't know me, so I'm Dr. Luke Fountain. I'm from the UK, so I am a molecular biologist by training. I've done a master's degree in molecular biology with a special focus on plant molecular biology. So I've done a lot of work on improving drought tolerance in crops, particularly looking at stomatal biology. I have a PhD in plant and soil science, so I kind of moved into the agriculture sphere when I started my PhD. And that was really when I started learning about controlled environment agriculture, or CEA, and found it absolutely fascinating, and wanted to pursue that. So, but I've also been a lifelong space nerd, space fan, and it's learning that we've been growing plants in space for the last decade is incredibly exciting, and has led me to where I am now, which is so I'm a postdoctoral fellow now, a NASA fellow at Kennedy Space Center. So I work in the space crop production team. So we do a whole bunch of different stuff, but we really look at the veggie system and the APH system on the International Space Station. So I'm sure we'll discuss more about those as we progress. But just kind of, if you're not familiar, a brief overview. So we have two plant growth systems in space at the moment. So we have the veggie system, or the vegetable production system, which launched first, and that is really like a control greenhouse, essentially. So it has a bank of LED lights, and so they're red, blue, and green, but it doesn't control the environment. It uses the cabin air, and with that we have very high CO2 and all these kinds of things that we have to consider. So I'll not talk about that now, because I could talk about that all day. I'm sure we'll discuss about that in the webinar, and the challenges that we face. But we also have more recently the Advanced Plant Habitat, the APH, and that really is a plant research facility that we have on the space station. It has over 180 different sensors and controllers, allows us to control the cabin environment, the environment that we grow the plants in, to really start to understand how plants are adapting to the space environment. So kind of two different things there, but that's broadly what we focus on. We also do a lot of ground-based research. So my research in particular focuses on optimizing nutrient uptake, particularly nitrogen, for the space environment, particularly at high CO2. So I'll kind of leave it there. I think I have another slide, maybe. I don't know if you want to move to that slide, but yeah, I mean, this is I've just basically talked through all of this. So so I have a lot of experience working with different hydroponic systems, which has been a kind of a fundamental aspect of my nitrogen research for a few years now. I've also worked with Alexei in the past, one of the other panelists, who I'm sure we'll talk about more about this collaboration in a minute. But so we built a small class of low-cost plant growth cabinets that you can see on the bottom left of the slide, and these are really a tool for outreach. This was our first foray into this kind of research, and really highlighting that actually a lot of the technologies that we think about and that we use in space actually are applicable on Earth, and maybe we can use this lens of human space exploration, which I think everybody here agrees is incredibly exciting, to get people talking about controlled environment agriculture and how it can help us solve the challenges that we face on Earth. So yeah, you can see, I've just highlighted some of the different systems I work with now. I currently work with lettuce. I've worked with rice in the past, barley, Arabidopsis, all kinds of things. And yeah, and that's kind of where I'm at now. So I'll leave it there because I've already talked for too long. But thanks again, and yeah, look forward to chain.
Thanks, Luke, for your introduction, and congratulations for the great work that you are doing. It's a pleasure, a great pleasure to have you here with us. Now I move the word to Tarun. Tarun, the floor is yours, my friend.
Thank you, Davi. As Luke was mentioning earlier, I've seen the efforts that you have put to make this happen, and finally super excited to see this take off. And on to what I do. I am currently a PhD student at Politecnico di Torino in Italy, and I'm getting my aerospace engineering PhD from there. And the project that I am working is in conjunction with Thales Alenia Space in Italy. And we are currently working on designing and developing an entire system for analyzing the life cycle costs of developing a bioregenerative life support system and growing plants in space or other planetary surfaces is an important crux in understanding the costs aspect of this entire thing. And that has essentially been mine and also Davi's passion project. And we've been working on something similar for a while now. And if you guys want to check our work out, we have published back in 2022 at the International Conference of Environmental Systems called Bridges. It's about the technologies that we use to upgrade the existing physicochemical systems to a more bioregenerative ones. And previously, I have my master's from the University of North Dakota in space studies. And from the comments, I actually see that someone mentioned about the SpaceAg conference, which also does the space agriculture. And I was there when the first SpaceAg conference was held at the University of North Dakota in April of 2022, I believe. And ILMA is the Integrated Lunar Mars Analog Habitat. And I was helping Travis Nelson, who was and is the manager of the analog station at the University of North Dakota. And I was also an analog astronaut and I have some experience working on plants in the analog environment. And can we switch to the next slide, please? So as you can see that the ILMA analog habitat is the one that you see on the left out here. And it has the dimensions and the area pretty similar to that of the International Space Station. And it has pretty much everything that astronauts would actually require in space. And we tried to recreate that kind of experimentation down here on Earth. One of them is the exercise module. You have the science and geology module. The center longest one that you see is the human habitation module, where you have the living quarters and the kitchen and the bathroom that is required. And you also have the plant production module and the EVA module on the other end. And you can see the EVAs that we do, the extravehicular activities are done in different spacesuits, as you can see over there. We conducted quite a few plant experiments throughout the different missions, one of which I was a part of. We grew microgreens in a small amount, but the other experimenters essentially also had access to seeds that were tomato seeds that were grown on the Mir station back in the 80s. And these seeds were then transferred to the International Space Station, I believe, and exposed to radiation for about 20 years. And when they were brought down, we tried to grow those tomatoes to see how potent these seeds were after being exposed to so much of the radiation and everything. So quite a lot of experiments going on here. And as for my experience in the biomedical engineering, you can see that I was working on everything that is human related, which is understanding the cognitive capabilities of astronauts while in space. Uh, all of these things tied in together essentially led me to what I'm currently doing, and my future interests and the work with Luke, Alexei, and Davi will involve developing cabinets that essentially are important for growth of plants in space. And we will be soon testing those things here on different analog stations across the planet as well. And thank you. On to you, Davi.
Thank you, Tarun, for your introduction. Very, very great experience, like exciting one. Becoming an analog astronaut, right? So hopefully in the future, astronauts, real astronauts. So Alexis, now the floor is yours. Feel free to introduce yourself and show what exciting you are doing with robotic systems.
Hi, Davi. Thank you, Davi and David, for inviting me here. So my name is Alexei. I'm a plant scientist. I did plant science at undergraduate, then went to Norwich to the John Innes Center to do a master's in plant breeding and biotechnology. I stayed there and did a PhD in molecular genetics on Arabidopsis. And then I wanted to try my hand in industry. So I worked for the plant breeding company Limagrain for a while, researching microspore embryogenesis, which the biology is very interesting, but I wanted to return to academia. So I moved to Sheffield to do a postdoc on the genetics of rice resistance to striga, a parasitic plant that infects a whole host of grasses and crops in sub-Saharan Africa. During this time, I had been growing many different species in different growth chamber technologies, some old ones, some walk-in chambers, reach-in chambers, and also at home playing around with microcontrollers and LEDs with a good friend of mine, an electronics engineer. So at some point we decided to maybe try and develop our ideas into a company. So in 2018, we started Robotic Systems with the idea of making a new type of highly instrumented desktop plant growth chamber for plant science research. So we played around for a while, we rented some space, and then we were successful in a Innovate UK grant with the University of Sheffield Fraunhofer Center for Applied Photonics and the Stockbridge Technology Center to do to carry out a multi-year research project developing our plant growth chamber technologies. Davi, could you move to the next slide? So here are some examples of those technologies. In the center, the cartoon is a sort of representation of how we see they might be useful in the labs. So they are small, they fit in and around the lab. They have very uniform growth conditions in the chamber. They have sensors and cameras, etc. At the bottom left is the first one we sold to scientists at the University of Leeds. Top left are some that we sold to a vertical farm startup. The bottom right are the two more advanced chambers, which have multispectral LEDs and are larger, so you can grow more growth area and taller plants. And then a few years ago, I met Harry and Luke at the University of Sheffield, who were very interested in growing plants in space. And together we made a modified version of a sort of flat pack chamber that I had developed earlier to test this foam, this hydroponic foam that Harry is developing was developing as part of his PhD, and I think continues to work on it now. So that's in the top right. Yeah, so I'm a plant scientist with, but I played around in sort of being an engineer and building these chambers, I'm very interested in controlled environments. Now we are still continuing with this, but we're also looking at building systems for home and for schools, and like Luke said, for this this outreach, kind of combining the idea of growing plants in space with growing plants in a school. Yeah, so I think that's it for me.
Thank you, Alexis. It's very uplifting to see like all the efforts that you, together with Luke and Harry, have been doing, and like seeing those cabinets hopefully applying soon in the analog stations around the world. It's like another exciting experience that we now are sharing like as a goal in our collaboration. So congratulations on the very meaningful work that you are doing with them. So, well, thank you for the introductions, each one of you. It's very great to see what you are doing from different fields. As the public can see, we have professionals from different backgrounds, but collaborating with one main goal, the future of farming in space. So that's why let me introduce you a bit of what is the space environment. Then we can start a better discussion on this. But as you can see, just for comparison, we have at least the idea of growing plants in space in 3 different scenarios. First one is the International Space Station. Then with the Artemis mission, we aim to reach the moon and start growing plants there in a long-term manner, building self-sustained habitats, lunar habitats. And after that, the next step is going to Mars. Each one of these environments has its own specificities and also its specific challenges. And some of them you can see here in the numbers provided in the slide, such as distance, gravity, and the temperature range, because we also can consider that space is a very extreme environment. With that, considering all of this scenario, as you can see, I would like to invite the panelists to answer the first question. What do you envision for the future of farming in space? What are your expectations? So if Alexis want to start, then we can start going to the others, or if someone else wants to start answering the question, feel free.
I can start with a few things that I'm sort of excited about, or areas of research which I think I'm excited about. So as I said, my background was in plant breeding, and at least 3 or 4 years ago, I think there weren't any plant varieties grown in vertical farms that had been bred specifically for vertical farms. And someone please correct me if this is the case. I know now many companies are carrying out breeding, but the idea of trying to develop varieties which are smaller in stature, have a higher harvest index, that is biomass that is usable or edible, better water use efficiency, maybe responsive to lower light input, faster cycling, all of these kind of sort of miniaturized plant structures or growth habits. I'm very excited about that, and especially combining it with genetic modification, if that's acceptable in space. Yeah, so I think that's one thing I'm very keen about.
So I can jump in next if you want. So yeah, I agree with Alexi. That's something we talk a lot about here is, the potential for genetic modification. And I guess, one thing I'm really excited about with that is, and some work has already been done in, reducing lignin content, things like that, to allow the non-edible biomass to be broken down more easily. Because certainly in the microgravity environment, referring to the slide, the lignin is really there to provide structural support against gravitational forces plants experience on Earth, right? So when you're in microgravity, you don't need that. So you can get away with removing some of that lignin and still have, plants that perform well can support themselves because of that lack of gravity. But interestingly, that kind of also feeds into the kind of tech that I'm most excited about, I guess, in the space field, which is one of the major challenges actually that we really have with space crop production, is nutrient recycling or closing the loop. Biological life support systems and recycling. So, thinking about how we can make systems more sustainable by recycling these nutrients is a big area of research, and there's a lot going on here at Kennedy, in various other places that are looking at that, and my work kind of feeds directly into that, with looking at nitrogen, closing the loop for nitrogen. So I think the other kind of aspect of that is very interesting is at the moment we lack an efficient way to monitor the nutrients that we are providing to crops in real time, right? And that's not just a space thing. That's the case in vertical farms, really any kind of controlled environment agriculture. We know what we're giving to the plants, but once we give it to the plants, we have no real way in real time of being able to assess how those levels change. And then because we lack that, we lack the ability to then dose those nutrients back in. So that's something that we're working on a lot. That's another thing I work on, using ion selective electrodes to monitor these nutrient concentrations in the nutrient solutions in the hydroponic systems that I use. But they are very difficult to use. They are incredibly difficult to use. And we're experiencing a lot of issues. And I would not say that I'm at the point where I'm confident that I can trust those readings. So we spend a lot of money at the moment and a lot of time, right? I spend so much time in the lab, analyzing ammonium concentrations, nitrate concentrations, using chemistry, right? Because we know chemistry works. So using colorimetric methods where the color change is dependent on the concentration. Those are great, but automation is limited, particularly in a space environment, right? And you can't have all of the hands-on crew time that you would like, because the astronauts are there to do the mission, right? Plant growth is never going to be the focus of the mission. It's a means to an end. It's a way for us to supply food to the astronauts while they're on these longer missions, when it's no longer possible or practical to send food from Earth. So I think that's kind of the major piece of technology that I would say I'm excited about, is trying to track these nutrient concentrations and then figure out how we can provide those nutrients, whether that's from adding fresh nutrients or by closing the loop, which I think is the only way forward, right? And CEA on Earth, we want to close the loop as well, make systems more sustainable. So,
Tarun, do you want to jump? Or if I just want to point out one thing previous, then you go further. Like, considering your background as an analog astronaut, this is also one point that we can consider. Like, together with all of this for the future of farming, it would be good for you to mention also not only the perspective of growing plants to be like a source of food, but you can also add something related to the psychological impact of having plants in a confined space, such as in a space analog station or even the International Space Station also.
Thank you, Davi. Firstly, I would like to acknowledge the importance of what Luke just mentioned. We do not currently have a significant way of like recycling the wastes that we have, especially when it comes to something that we grow out there. We're carrying a lot of nutrients, and we're carrying a lot of mass with us to space, which costs a lot of money. And then we don't know how much of each of these resources that we're carrying up there is being used by each of these plants and each of these other entities that we're trying to grow in space. And as an example, we could just assume that, okay, let's on the APH, we tried to grow wheat, and and we also tried to grow lettuce at the same time. We know the nutrients that we get from wheat is significantly higher in importance for us as humans than what we get from lettuce. But at the same time, we also need to know that wheat, although is very important, it produces very less usable mass, and there's a lot of inedible mass that we don't know how to reuse or recycle at this point of time. And being able to convert all that mass that we just produced in space in a significant way is super important. And this then leads us to the psychological aspect, which again, we are trying to test all of it out by different modes of experimentation here on various analogs across the planet. And the short answer is this: we still don't know quantitatively. We have never figured out exactly, using data, there is no scientific proof that plants are actually psychologically helping humans in isolated environments, which is kind of unfortunate if you ask me. But we're trying to change, with Davi, Alexei, Luke, and Harry, and the other team members here. We are trying to obtain enough significant data to essentially say exactly what is going on with human in the loop in isolated environments like that. And as for technologies that I'm super excited about, identifying how exactly can human benefit from the growth of plants other than direct impacts, which is food related, is right up there with the food itself. And one of the things that Luke was mentioning about, I think he was talking about the nutrient control and the nutrient recycling stuff. I would actually say that we tried to do a similar thing in the analog at ILMA, which we could not figure out by the end of it, of course, by essentially saying that, okay, we put 100 ml of this particular X liquid for this microgreens to grow in a certain way. And we wanted to check how much of it was used by the end of 7 days. Some of them essentially took about 9 days to grow. So with so many variables in there, we weren't able to determine exactly what and how things changed. So that's one of the things that I would like to also see happen in the near future. The last thing is the placement of understanding the human factors behind where these plant growth chambers are most beneficial for humans' psychology is also not very well known. So I would like to see significant progress made in that direction as well. That is all I can think of for now.
Great. Go ahead, Luke.
Yeah, I was going to just jump in just to pick up on a couple of points that Tyrone had mentioned. So the first one is that interesting wheat lettuce comparison, and that's a very interesting point. So what Tyrone said about the amount that you get out versus the amount that you put in is incredibly important. We also have to factor in things like take a holistic view. Look at the downstream processing, right? You cut the leaves off a lettuce plant, you can eat them, right? But you can't do that with wheat. Well, you can, but it wouldn't taste very nice. There's a lot of downstream processing that needs to happen before you end up with a product that you can actually use, that the astronauts can actually consume. And one, how are we going to do that in space? Is it feasible to do that in space? And two, is it worth us doing that in space? Those are the other kinds of things that we need to think about. And you can, lettuce is a cut and come again crop, right? You can cut it 2 or 3 times, let it regrow, come back to it, cut it again before you actually have to, bin it and start a new grow out. So All these kinds of things we still have to factor in as well. And yeah, and picking up on the psychological aspects as well. I think that's incredibly important. It's a very difficult thing to measure, to quantify, to characterize. But when astronauts grow in space, they always fill out surveys. It's a very, very small sample size, but it's always, yay, we loved having this fresh food. We felt better for looking after these plants and eating this fresh food. Particularly when PHO4 happened, when we grew chilies and they had space tacos. That was pretty cool. All these kinds of things. So I think there's a question in the Q&A that was, if you could only grow one crop on Mars, what would you grow? So my answer would be chilies to that. Martian tacos sounds pretty good.
That's great, Lou.
Okay.
Well, yeah, David. No, I just want to mention that for those, I saw that there are some questions in the chat. So if you want to address these questions on the Q&A, it will be better for us to track. And then I think we can start the Q&A now, David. What do you think?
Yeah. So one of the questions that we have from the audience is about lunar and Martian soils. So I guess the first thing would be if someone can tell us a little bit about, what are lunar and Martian soils like? Do they have similar nutrients to the soils that we find here on Earth? I guess that would be the first part. So if one of the experts can please go ahead.
Yeah, I think Luke is the best, the most suitable. Just go ahead, Luke.
I have some pretty strong opinions about this, but no, of course, I'm happy to take that. So, so growing in lunar and Martian regolith, that's kind of the, regolith is the buzzword in space crop production at the moment, right? I'm not a geologist, so it's probably better to talk to a geologist about the actual components of lunar and Martian regolith, but I can point out from a biological perspective some of the things that are important to consider. So the first being that there are not many nutrients in either lunar or Martian regolith. It's nothing like terrestrial Earth soil at all. And there are a lot of additional complications. So, for example, the one thing that makes soil so good for growing plants is the microbiome. The soil microbiome that is present, they form symbiotic relationships with plants. Plants provide a lot of the carbon, and in return, they get nutrients that are foraged by these microbes. And there's all these kinds of interactions going on. And we know that these microbiomes help improve plant growth. Now, of course, at least we kind of figure at the moment that those do not exist in lunar and Martian regolith. So instantly growth is never going to be as good, irrespective of what is present in the lunar and Martian regolith. So a couple of other sort of important things to note, particularly Martian regolith, is filled with perchlorates, which are toxic to plants. So we have to have some way of dealing with perchlorates before we can consider growing plants in Martian regolith, whether that is through chemical treatment, some kind of biological treatment that we could think of, that can break down these perchlorates, use these perchlorates perhaps, to condition the regolith before we grow for plants. So they're kind of the 2 points. In respect to lunar regolith, the additional thing that we have to consider with lunar regolith is that there is no atmosphere on the moon, right? So there is no weathering. So all of the lunar regolith is formed. This is a biologist's simplistic overview of this. So I apologize if there is anybody in the audience who knows more about this than I do. But really, the issue is that a lot of the lunar regolith was generated by millions and millions of years of impacts on the surface of the moon, right? From asteroids and debris and all these kinds of things. So you get this fragmented, really finely ground lunar regolith, right? But it's incredibly sharp. So it's not like sand, which is weathered and it's rounded and it's kind of soft. It is incredibly sharp. And when we went to the moon for Apollo, that was really, really difficult. It would interfere with the seals on spacesuits. It was covered in spacesuits. It was, in the habitat in the lunar module. It was a nightmare. So really, my opinion is that at the moment we want to be doing everything that we can to keep that stuff out of our habitats, right? And I think my honest opinion, I think the opinion of most people here, to be honest, is hydroponics are the way forward. So, you know, that's not to say that we can't grow plants in lunar regolith. We absolutely can. You know, Annalisa Paul, Rob Firl managed to do it in actual lunar soil from Apollo 11, Apollo 12, and one of the other Apollo missions. I can never remember the third one, but so it is possible. And you know, there are lots of people that are growing in lunar regolith simulants, what we call simulants, which are pretty accurate based on you know, the geological data that we've collected over the last few decades. So this research is definitely ongoing. There are a lot of people that work on it, but in my opinion, too many people that work on it. Not enough people that work on optimizing hydroponics for lunar, you know, for lunar greenhouses, for even for growth on the ISS, right? And whatever commercial space station replaces that in the next decade. And you know, the gateway, the lunar gateway that we're building at the moment, that's going to go in orbit around the moon. Probably not going to have a plant growth facility on there, but who knows? Yeah, maybe in future. So you know, but all of these are going to be hydroponics. And that's not to say that regolith is not important. We're not going to use it in the future. I think if we're going to expand plant growth in the future, absolutely we need to think about using the resources that are there. But that's decades out. So I kind of tend to stay away. I stay interested in it, but kind of stay away from it at the moment. But that's just my opinion. So
I just want to complement this on what Luke said, is that I think it's relevant for us in general to think that in space we are dealing like with a risky missions. Like astronauts, they are risking their lives to go to space for scientific development. So this food will be a vital system. So if we have different solutions to grow food, they are most welcome. So it's not only one solution or the other, but we must integrate this in the best way as possible. So David, do you have any other question from the public?
Yeah, so we had another question, and I think this one, Tarun answered it in the chat, but Tarun, if you could answer it on the webinar. The question was, how do you mimic variable gravity and its effects on plant gravitrophic effect on Earth? So maybe you could explain this a little bit more. Thank you.
Sure, thanks, David. So clinostats are devices which have just the rotating, it's just a rotating plate that is held perpendicular to the gravitational force. And you just grow the plants at the center of that plate itself. And because of the rotation of this plate at I can't remember the exact RPM that it needs to rotate in, but that effect essentially cancels out the gravitational force that is acting on this plant. And we essentially end up growing a plant that is vertical in the perpendicular from gravitational direction. And that is the best simulant of micro G that we have here on Earth. And it works very accurately to what it actually should be for an actual space-based thing. So you can just Google clinostats. There's quite a few commercially available clinostats available that you can just buy off the shelf, and you can test it at your own house, or you can even attempt to build it so you can get better understanding of everything that's going on in there. I hope that answers. If there's any further questions, please feel free to just type it out.
I was just going to make one small point there. So my understanding is so important distinction here. So that there is no way that exists to actually get rid of gravity, right? Other than fly out of low Earth orbit, right? But not low Earth orbit, out of the gravity well. But what the clinostats do is they continuously move the plant so that it is never in one position for long enough that it can actually perceive which way is up and which way is down. So we're not actually getting rid of the gravitational effect. What we're doing, we're tricking the plant into thinking that there isn't, because it's never in a position for long enough to determine which way is up and which way is down. So in general, Yeah, yeah, and like you say, in general, it's a pretty good simulation, and if you compare, data sets from those plants to data sets of plants growing in microgravity, there are a lot of similarities, but there are also some differences as well. It's not always the same, so it's just a minor point there. But yeah, they're a pretty
Okay,
good
great.
tool.
Yeah, thank you for that clarification. One other question we've had several people ask about is, and Tarun, you mentioned this early about an experiment where I believe you mentioned tomato seeds going up into space for a portion of time, and then those crops being grown on Earth. I've also read about, I think, some buckeyes or other trees that have gone to space and been planted on Earth. So I have a question here. It says, what are your thoughts on having plant research done in space that could support Earth agriculture? For instance, I believe bringing seeds in zero gravity can unlock new genomic traits to support new breed varieties. So I guess the question is, have we seen any impacts from taking plants or seeds or plant material into space and returning it to Earth? What are those impacts that we've seen? What can we learn from these experiences?
Um, uh, Thank you for the question, David. But I know the engineering aspects of it because that was my background. But I think a better person that is suited to answer this question would be either Luke or Alexi. So
I think
if you guys
Alexi,
can please just hop on and help me out here, that would be a fantastic thing.
yeah.
Yeah, no, I can start, and I think Alexi will probably be able to say more from a plant genetic point of view. So, one thing that I am aware of is, so yes, absolutely, this kind of research goes on. So we have experiments that have been done here where we've sent seeds up from KSC, exposed them to radiation on the outside of the space station, and then brought them back and grown them and see what happens. They grow, so which is pretty remarkable, to be honest. It's very variable. So sometimes they perform just as well as plants that have been grown that have not experienced this radiation, and sometimes they're severely affected and severely stunted. So it's kind of a very variable effect, and it's still quite a difficult thing to do at scale. So that research is ongoing. But interestingly, the Chinese have actually done the same thing, but they actually use it instead of so. I'm sure most people here are familiar, but the common way to look for new traits in plants is to fire a little radiation at the seeds, grow tons of different plants, and then look for traits of interest, right? Through using the DNA to break using the radiation to break the DNA that's repaired, but it's not always repaired efficiently. That can cause genetic changes, which can manifest in phenotypic changes. The Chinese, instead of shooting plants with radiation, actually take the seeds to space, expose them to radiation for a few months, and then bring them back and then do those trials. So it's not quite clear if anything different happens when you do that, but it's certainly a novel way of doing it, which I think is pretty cool. But that's kind of one example of how that kind of research is done. Yeah. So I don't know, Alexi, if you want to say anything. I don't want
to. I'm not familiar with any research. I mean, there is some fundamental research being done, both on like lettuce, but also on model plants like Arabidopsis thaliana. I'm not quite familiar with what kind of stuff they have been doing, but like Taryn said, I mean, a lot of the engineering technologies. So I think NASA in the 80s was probably one of the first organizations to start using LEDs for growing plants. And also, I think maybe they had one of the first sort of vertical farm style systems. So, I mean, that wasn't done in space, but it was done for space. In terms of the radiation, that's interesting. I wonder if there are different types of radiation cause either like large or small breaks in DNA. So I wonder if like bringing seeds up into low Earth orbit causes different types of DNA break that might be more useful than like putting it than bringing it to a nuclear reactor or however they do it now. But it also seems quite expensive. I don't know if the benefits outweigh the costs.
Okay,
Yeah.
thank you. Anyone else want to
David,
comment?
yes. I hope that Luke and Alexei essentially answered the question, because I was going to go here on a little bit of a tangent about the engineering aspect associated with this question, which is because these seeds are essentially exposed to significant amount of radiation, and they are firstly grown in a completely different environment than what these plants were intended to grow in, which was on healthy earth gravity, the good sunlight, and all the resources as and when they needed was usually taken care of. But all of these things are usually measured and try to understand, like people, like there's a lot of scientists that are trying to re-engineer the seeds so that they can be better suited for different environments across the planet. So research like this and having the data about the radiation exposed seeds versus the regular seeds and how the growth rates differ versus the different kind of mutations that occur within the seeds technically help uh, the engineers like design better equipment to shield, maybe reduce the amount of radiation slash improve the systems that can deliver the nutrients required by these plants, etc. So in a way, they are helping different fields grow in different ways. And one of the things that, yeah, this is, I would like to add this as one of the key things that I'm excited about for the future technologies for space farming. And I think someone else was asking about the radiation stuff in one of the questions too. So thank you.
Well, we are just about out of time. I would encourage all our panelists to either include their contact information in the chat or their LinkedIn profiles, so that if people have additional questions, they can reach out to you. Davi, I know we are going to give a discount code for the Space Farming 101 course. So if you could want to share that slide now, that would be great.
Okay, so jumping in. Well, for those who have remained until now, as promised, we have a special discount, especially to recognize that you are putting your time into it to see what these amazing researchers, professionals are doing in the space farming field. So we have a few questions that were not addressed. Specifically, I can mention some of the technological ones regarding LED lightnings, greenhouses, vertical farm. And I can let you know that this is all covered in the Space Farming 101 course. As I mentioned, this is a course with 4 lessons, 14 modules, and a lot of practical examples. Not only for you to know more about the space farming research, but the idea of the course will be providing you directions on how you can utilize this technology that is being developed and it is evolving in the space farming sector, and showing you how you can utilize this here on Earth on terrestrial agriculture, specifically in the current modern agriculture systems, such as indoor farms, vertical farms, and so on. And the 2 dedicated studies will be presenting you more details about what is being done into the topic. Well, now let me tell you that the course itself, the regular price of the course will be available, can be you can have the access for the course by $79 USD. But for today, during this webinar, we are offering you a special condition of launching the course, which is 67 USD. So as you can see in the slide, we have the coupon in which you can just add during the payment process, and you can have access to the course by the value of $67. And it's worth it to mention that this coupon will be valid until Friday on the 5th of April. So, and if you are asking how you can purchase the course, how you can have access to it, let me provide you a quick step-by-step process on how you can do this. First, you should access the architecture design website, as you can see in the slide. And well, in the top part of the website, you have the premium content window. So once you click it, you see the initial this initial screen as is shown in the slide. And after that, you can just click to get access of the course. Then you'll be directly to sign or register yourself. After doing the registration in the Architecture Designer platform, you'll have a new window opening for you, specifically the one related to the platform itself. And then you can check on the Knowledge Hub, the premium content. The same window will be appearing to you, and you can have access directly. It will be showing the necessary steps for you to purchase the course and utilizing your registration credentials to access the course for 1 year. And if you are still in doubt and want to check what the course will be presenting to you, let me tell you that we have some previews available to you. So once you click on it, you can see all the lessons available with the modules. However, only in the lesson 1, you can have access to the module 1, showing what you need to know about the Space Farming 101. And this video specifically, you have access to watch the full video. And well, that's all. Since now, I want to welcome you all to the Space Farming 101. And I really want to thank you for being present here. And also, I want to invite you to join us in this exciting journey towards growing plants in space. Thank you very much. Thank you, David, and thank you for our invited speakers for being present today here.
Thanks very much.
Thank you both. Yeah, thanks everybody.
Thanks,
Thank you,
everyone.
everyone.
Have a great day.
Have a great day.